So today we're going to be talking about diffraction. Now, we're going to expand on what we did last time on the double slit experiment. And really, the double slit experiment could fit in this topic just as one example, but it's an important enough example that I made that like its own topic. But the idea is, say you have two sources of waves, say S1 and S2, and then you have some point P. So we can look at the distance from each source to that point P. We'll call those D1 and D2. Now we have to make an assumption that the waves coming from S1 and from S2 are in phase with respect to each other. So we're just going to make that assumption throughout the whole thing, throughout the whole class. So these two waves are in phase when they start. And what kind of interference are we going to get at point P? And the general result is, what we do is we mark off a distance from along this line from point P to here, so that this distance from here to here is equal to D1. And whatever is left over, we call that the path length difference, delta. And so the condition, I'm just going to write this down for both cases. Okay, so the condition for constructive and destructive interference are shown here. So, m can be an integer, including 0, or a natural number, including 0. And I'll make sure that that's all visible. Yeah, so if delta is equal, if we plug in m equals 0, we get like the basic condition. If delta equals 0, then these two waves start in phase, and they travel the same distance, so they're going to end up with the same phase. So delta equals 0 is definitely constructive interference. And if they're half a wavelength out of phase, so again, let's look at a wave, just have a nice sine wave. So again, if you have two that start out, say, at 0 going up, if one of them travels through half of a wavelength, if you compare these two, they're exactly out of phase with respect to each other. So if one travels an extra half a wavelength, then when they meet up at point P, they're going to be exactly out of phase and interfere destructively. So those are the basic conditions when you set m equal to 0, but you can always add a full wavelength without changing anything. So if you add a full wavelength to just move, that's adding an entire wave that doesn't change its phase at all. So again, you can apply this to double slit experiment and find the condition for constructive and destructive interference from geometry. So again, this is nothing new, but we're going to look at a few more examples of diffraction. The double slit is very important historically, and it definitely deserves its own topic. But let's look at, we're going to look at two examples of diffraction, or 2.5 anyways. One is a single slit. So before we had those double slits, there are two very narrow and very close together slits. This is something more where there's a width involved. We'll say W is the width of this opening. And we're going to shine this light on the screen. And this raises the question, how is light going to behave when it passes through this barrier? So if we look at it, if we have a wavefront, or a series of plane waves that just keep traveling, you might think that when it goes through, it's just going to look like this, which I think I mentioned this in the last one. This is definitely not the case. So it's not just that these barriers block off the part that, that actually hits it, and the rest just continues through. That's just not how waves work. So what happens is they spread out. These waves spread out. And again, there's some good pictures and even videos where you can see this with real, actual, like water waves. You can actually see diffraction, where you have these waves coming in, they hit a barrier, and then they spread out. And yeah, so that's diffraction. Now, how does this happen? And the answer to that is fairly complicated, but it's better just to erase it and redraw it. The idea of wave propagation is actually a pretty complicated thing. Like, say you have a plane wave, and you know this wave is going to be moving. How is it going to move? Like, what's it going to look like after a certain amount of time? Again, that's actually a very complicated question. And one of the earliest explanations of how waves propagated was by a guy named Huygens, or not sure if I'm pronouncing it. I think it's Huygen. This guy worked with Isaac Newton, so it gives you an idea of the time frame. And this is one of those things, I have no idea how he came up with this. But we talked about spherical waves as well. So spherical waves, they just keep producing spheres that expand outwards. And a plane wave is basically, if you're far from the source, the curvature is insignificant. But what Huygens, the idea he came up with, is that we treat every point on this plane wave as a source of spherical waves. Now, I say every point, there's an infinite number, but, when you go, anytime you deal with infinities, pretty much you're talking about calculus. So we can't go into this in too much detail, but we can approximate it. Just say there's a bunch of points. We can approximate a plane wave as just a finite number of points creating spherical waves, and we know how to combine waves in general. So we have like all these sources of spherical waves, and it is possible to show if you have a plane wave, that'll produce another plane wave, which will then produce another. So these plane waves can just keep propagating, but that's if they're very long. If you cut it off, so if you have like a finite plane wave, then it's going to spread out. Okay, and so what we're interested in is that example right now, where we have just these plane waves coming in, and then right at the barrier, here's our plane wave. The rest of it is blocked. So we have like a finite number of points. We can approximate it that way. And what we're actually interested in here is, where does the first minimum occur? Like, where is the first place where we will get destructive interference? So let's just say that's right here. So that's destructive interference at that point on the screen. And really what we want is this angle that's going to go from the center of our slit to the point on the screen where we get the destructive interference. So what I'm going to do is I'm going to draw a ray from the very top and from the very bottom. So I'll erase this angle now just to unclutter the picture. And we're going to compare rays from both extremes, the top and bottom, that are meeting at point D. And again, we're going to assume that the distance between the barrier and our screen is L. We're going to assume that L is significantly greater than W. And the reason why is we can consider these rays to be nearly parallel. Okay, so what I'm going to say, let's draw a line here so that these top and bottom are, like, from this point, like these 2 points are the same distance from point D, or that point on the screen I label D for destructive interference. And what I'm going to say, and then I'll explain why that's the case. But what I'm going to say is that to get destructive interference, we want the path length difference to be equal to lambda. Now that might sound a little surprising because right here, if we set m equals 0, destructive interference should be half lambda. And if we plug m equals 1, 3/2, delta equals lambda, normally we'd associate that with constructive interference. But that was looking at this particular situation where we have only 2 points. Here we have an infinite number of sources of waves. So, it's not a contradiction to say that in this case, if this particular delta is equal to lambda, we get destructive interference. Now the question is, how do we know that that's the case? So I'm going to draw this triangle here and just expand it a bit. So let's say this is our right angle here. This is lambda. This is, let's label this point A and this point B. So we have the top of our opening and the bottom. And then we've got these rays going, meeting up. Basically, we're treating these as parallel rays because L is so much greater than W. And they're going to meet up on the screen. And if these two are off by lambda, let's look at a point right in the middle. And say this ray is going to point D on the screen. So we have a triangle here. And if this is the midpoint between A and B, then this segment here is going to be half of this segment, this side. It's just similar triangles. They have the same angle. And so if you double this side, they're similar triangles. So if this is half of that, then this one's going to be half of that one. There's similar triangles. And so we can see that these two rays are going to be out of phase. So they will interfere destructively. And let's look at a point a certain distance x beneath point A. And similarly, a distance x beneath the midpoint, let's label that M, these two rays are going to have the exact same relation. And so these are going to interfere destructively. So you can start at point A and the midpoint, these two interfere destructively, and then just look at each point below A, there's a corresponding point beneath the midpoint where they interfere destructively, and so we're going to, everything is going, when we add up the sum total, they're going to come in pairs that cancel each other out. And so we get this destructive interference if we have this, this condition here. So we mark off these 2 points are equidistant from D. So a path length difference here is lambda. That gives rise to destructive interference. And remember, this angle here was theta. So if we draw this parallel line, that angle's theta, which would also make this angle theta. And so looking at this triangle, we can say sine of theta is lambda over W. So opposite over hypotenuse. Hypotenuse is across from the right angle. And so our condition for destructive interference. So this is a thin slit. this is destructive interference. Sine of theta is lambda over W. Okay. Now, okay. Now, that's just destructive interference, but what does, let me see what this, I think there's a picture in here. Yeah, so what we'd get by shining light through a slit like this, there's a picture in the book up here that kind of shows, like, right across from the slit we get this bright fringe. So it's a very lit up area. And, see if I can hold this. If you look at, say, like right here, or right there, that would be, so like, this would be our destructive interference, and then we have another bright fringe, and then dark and bright. Kind of looks like the double slit, except the details are very different. The central bright fringe is very, very bright. And then we go to 0, that's our dark fringe, and then we have another bright fringe, but it's very dim compared to the central. So basically, you can think of it almost like if you didn't know anything about waves. You shine light through, most of it falls right across the screen, but you do get that little interference pattern. Let me bring this picture up one more time. I guess the point is that most of the energy is directed in this central bright cone, which would be, you know, basically, it'd be better if I just redrew this entirely. So here's our slit, here's our screen, and basically the energy is directed in this cone that makes an angle theta with, you know, from the center of the opening to that first minimum. That's where almost all the light is going. And so, yeah, usually it just spreads out, and you know, this angle gives us a good idea of this cone that's coming from this opening. And this is for like a rectangular slit. So, yeah, if you have like, say like this whiteboard, if you just cut a vertical slit through it, you know, the light would spread out going through the slit. That's called diffraction. And again, that is a property of all waves. It's impossible to avoid diffraction. So this thin slit, yeah, that's one example. Mainly we do it because we can calculate this. One thing we should notice, you might have remembered sound waves, they're waves, so we should expect the same thing. And yeah, we get the same thing with sound waves. And another very important but similar example, what if instead of like a rectangular slit, what if you have a circular opening? Or an aperture? So again, this is a very important example because it happens in nature all the time. Cameras, telescopes, you know, every type of device, or just your eye, your pupil is circular. So when you shine light through a circular aperture, you should get diffraction as well. Oh yeah, going back to sound waves, you know, I mentioned in sound waves, if you look at sound waves traveling through like an open doorway, that would be a good example of a thin slit. Doorways are rectangular. And so you should experience diffraction with sound waves. Now imagine you take a laser pointer and you shine a laser at the door. Are you going to see the laser beam spread out when it passes through this door? And the answer is, of course, no. It's going to look like it just keeps going in a straight line. Now, technically, it has to diffract a little bit, even passing through something like a doorway. You wouldn't expect a laser, this tiny beam, to be affected by a doorway a meter wide, and really it isn't in any noticeable way, but at a fundamental level, it is being diffracted. However, the effect is only really noticeable when the wavelength is comparable, or the size of the opening is compared to the wavelength. So if you look at sound waves that might have a wavelength of around a meter, they will be affected by passing through a doorway. Light, measured in nanometers, basically you're going to get sine of theta equals 0, which means theta equals 0. So you're not going to notice any diffraction, but technically sine of theta is not precisely 0. It's just going to be a very small number if you try to shine like a laser pointer through a doorway. And so theta will not be 0, but it's going to be so small you can't really notice it, at least just by visually shining light through an opening. You have to look for other ways of noticing these effects. So diffraction is really significant when the wavelength is comparable to the size of the opening. But now let's go to the circular aperture, and we get a very similar effect. We get this central cone where almost all the light goes. Now, actually coming up with the formula is very difficult. It involves calculus. You have to look at a plane wave, which is a two-dimensional surface, and look at each point and add it up. It's pretty complicated, so I'm just stating the result. Sine of theta is 1.22 lambda over d. So now that's the reason why we're stating this result is, of course, just because of the importance of it. Now, let's say we shine light. A very important application of diffraction, something called resolution. So let's say we have an opening here. And say we have a source of light. Let's say it's red. Or, we're going to have two sources. So again, you might think this is just a point. It's a very identifiable point. But what if we, shine through, it's going to diffract to some extent. So what it's going to look like, well, the central right across, so the peak is going to be right across from the center. Okay, so we're going to get basically all the energy. It's going to spread out into this cone. And how much it spreads out depends on the wavelength of the light compared to the wavelength of the opening. So if we have a narrow opening, we could get a much bigger spread here. If we have a bigger opening, it'll be a more sharp. Let me actually draw that just as these two examples. So basically everything is the same about these two except for the size of the opening. So here we might get something that just looks like this. Almost just a vertical line. It's going to be, and here with a wider opening, more diffraction. Okay, now what if we place a blue dot next to the red dot? So what we're going to get is something that looks like this. Where over here, if we place a blue dot next to it, we're going to get something like that. And what's different about these two cases is here, these two sources, what we see, these overlap to a very large extent. Where over here, we can clearly identify two separate sources, but here they kind of merge together. And so if this is just your eye, and you're looking at two sources, and again, now you can also imagine, what if you just move these farther apart? Then these are going to move apart, and they'll be identifiable as two separate sources. So resolution depends on how close they are and the size of the opening. But for a given opening, you'd have to move these to a certain distance before you could even see those as two separate objects. And so, this is the idea of resolution. Your eyes have a limited ability to identify objects as separate sources because of diffraction. So if the objects are very close together, then they'll overlap, and you will just see one, here, if you were looking at this, you would just see one dot. And what's interesting is the color would be a mixture of red and blue. I never learned colors, mixing colors, what you get. But, red plus blue, that'll give you some other color. That's what you'd see. You'd see a single dot that's of a particular color that you'd get from mixing red and blue. Where over here, you would see two separate dots. And there's a great example of this. It's actually in Chicago. Oh yeah, here's another example of resolution. And it's better to start over here. Here, these are the headlights from a car. And when it's far away, you just see a single light. But then as it gets closer, you can see, like in the last picture when the car's close, you can very clearly see those are two headlights. You can see it in the middle too, but far away, can't really tell. Looks like just a single light. Kind of another interesting example, if you go out at night and look up, a lot of stars that you see, about half of them are actually binary systems, where you have two stars orbiting around each other, but they're so far away that the stars are so close together that they just appear to be a single dot, even though there's two stars with some separation between them. But again, there's no way your eyes can resolve them. Some people are better than others at that, but yeah, now you can improve resolution though by making a bigger opening. So like here, like say these are two stars. Yeah, I'm going to mix this up. I think I got these backwards. Sorry, here, I should have had this one. See, it depends on the wavelength of light as well. But, yeah, so that picture I drew isn't necessarily wrong. It just depends on the relative wavelength compared to the opening. But let's say we're looking at astronomy here. And your eye is a very narrow opening. And so if you're looking at two stars, they're going to overlap. But then with a telescope, you can greatly enlarge. The telescope can have a much larger diameter mirror. And so with a telescope, much larger opening. So here, there's not much diffraction because we made the opening larger than the wavelength of the light. And so here we could definitely resolve these and see two separate objects. Where here, you can only see one. But yeah, I got distracted. I was looking for an example, which, yeah, here it is. Yeah, it's at the Art Institute of Chicago, where this is a painting. Seeing it, so yeah, it just looks like a painting. And the artists, normally when artists, they have the primary colors of paint, and then they, you can mix primary colors to get other colors, so that's what they do. So say you want one color on the canvas, you'd mix your primary colors to create that color, and then put it on the canvas. But the artist here was George Seurat. And instead of mixing the paint and then putting it on the canvas, what he would do is just use these primary colors of paint and make the entire painting nothing but dots. So there's only 3 colors in this picture, but again, it doesn't look like that. It just looks like an ordinary painting. And that's if you're far away. However, if you walk really close to the painting, then you can actually resolve these dots and see they're just these same 3 primary colors. But when you're far away, your eyes merge the nearby colors, or the nearby points, into a single source, and yeah, they mix, and so they can actually appear different colors. Again, I should learn this color theory stuff. I just never keep telling myself to do that. Or like, if you mix 2 paints, what are you going to get out of it? But yeah, I should just write it down, actually, instead of learning it. But anyways, hopefully you get the idea. So that's diffraction, and very important topic, particularly in astronomy, because you want to study things. If you were to look at, say, Mars, you can see that just by looking at it, but it just looks like a dot, basically. Like, you can't see Mars as like an object, because in order to do that, a spherical object, in order to see Mars as like an extended object, you'd have to be able to resolve the two different, you look at 2 points at the edge, you have to be able to resolve those as separate points. And your eyes are not capable of doing that. But with a telescope, bigger diameter, more light gathering, mainly it's just bigger diameter that matters in this case, you can get better resolution, and you can see a planet as like a disk. And so, yeah, that's diffraction. And again, this is just diffraction through like a significant, like a single opening, either like a rectangle or a circular opening. And so I think I'm going to actually stop the video here, and then we'll talk about something called the diffraction grating. But just to break it up into 2 chunks, I think I'll stop here and then record another one.